You all get silence before we start. That's good. Very welcome to this second session on the Bolin Days. And just a few reminders for those of you who are new, who didn't attend before lunch. So there is a room where you can watch this session with this screening instead. Streaming, sorry. And it's U29. So if you don't want to stand, you can go down, and it's streamed directly. And also this microphone is not because we should hear each other in here, it's because of the streaming. So when we pass it around, you have to talk into it so we get what you're saying, everyone. So nice to see so many of you here. My name is Regina Lindborg, and I'm leading the RA7 research area, and it's called Land Use and Landscape Processes and Climate. And this is Arvid.
Hello everyone, my name is Arvid Bring, and I'm co-leader of RA3, Hydrology, Cryosphere and Climate, Hydrosphere, Cryosphere and Climate, sorry. Yes, and so really glad to see so many of you here.
Okay, so this session is called Impacts of Extreme Weather Events and Climate Change. And I will start a little bit with a short introduction to this session, how we see this session coming about. As you can see in this graph, there has been a lot of extreme weather events on the rise the last few decades. So both the number of flooding, storms and drought has increased quite dramatically during the last 20, 30 years. And just during this year, we have seen many extreme weather events in Europe, for example, flooding and heavy rain in Greece and Italy, and also in other places. But in some areas, like in Venice, where we have severe flooding this year, they are prepared since before, but this has been quite extreme year for flooding events. And also here in Sweden, we have quite dramatic wildfires going on during the summer. And as you can see on the graph on the top, if you compare to a mean between 1981 and 2010, we are somewhere above 3 degrees warmer this summer than we usually are in Sweden. And we had quite heavy wildfires, so we have to take help from Southern Europe in terms of firefighting. And now we all know about this campfire going on in California, which is extreme, even for California circumstances. So that's sort of the background to this session. And we thought about this session to take us from more a global perspective on extreme weather events and to regional and also down to local, how people actually can work with these risks and prepare. And we will talk a little bit about process understanding and projecting impacts of these weather events and also associated risks for society. So it will be a little bit mix of everything, also at different scales. So with these words, we start, I think. And this is the agenda. You have it also on the paper that you got when you came in. And we will start with Erik Kjellström from SMHI. You're here. Yes. So
thank you very much for the introduction, and I'm also thank you for having me in this session. I think it's very interesting to talk about extremes. I was more or less given a title to give a general view, and I thought that sounds very interesting, and then I started to think about it in 12 minutes to give a general view on extremes. It's really a huge area. So I had to refine the title a little bit. So now it will instead be a very general view in just a few slides. Then I will give an example of one extreme event only. And then I will show some climate modeling results again. And while giving this example and the modeling results, I will also talk a little bit about some of the aspects you need to look into. But the field is, of course, extremely large, and but there will also be more presentations afterwards looking at other aspects here. So first, we can maybe just go back to this, what is an extreme event? This picture shows the front page of the special report on extremes by IPCC. It came out in 2012, I think. There they make some definition of what an extreme event is, and here they talk about occurrence of some value of some weather event or something above a certain threshold, and then they start to talk about different numbers that are usually being used in the literature. And if you look at these numbers up there, 10, 5th and 1st percentiles, I mean, these are often termed as extreme events, but if you think about it, the 10th percentile is something happening statistically once every 10th day, so it's not that unusual. It might be quite extreme in some sense, but it's often not that extreme. So you have to think a little bit about that. Other studies on extremes and the impacts of extremes might be interested more in a return period of 1 in 10,000 years or something like that, and that would be a more extreme event, in my view. Information is often building on observations, of course, but for the future we don't have any observations, so that we have to rely on models. And also for the past, the amount of observations is really limited. And also for the present climate, observations is sometimes very limited, and we cannot really say too much about exactly how these extremes are defined. So we need to rely on different sources of information. There are 2 points down here. I think it's also important to look at some of these climate extremes. They may not be extreme, all of them. I mean, this summer was a very good example. We had a long summer which was very warm here. But the number of days really being record high temperatures in Stockholm or in Sweden, for instance, it was not that big actually. There were a few occasions like that. But looking at the period May to August, it was really a very huge extreme, far out of any statistics that we have seen before for this long time period. So that's an accumulation over a long time period. It could also be rainfall every day, and then at the end of the year you have a large amounts of water everywhere. Finally, also you could look at different types of things happening at the same time that could create something which has a very big impact, and then you have an extreme event in the impacts. The windstorm Gudrun, for those who recall that one, it was a major windstorm, of course, but it was not completely exceptional. There have been many other such storms before, but it happened at the end of a very mild winter, so the grounds were not frozen, and all the trees in southern Sweden, not all, but many of them, they fell down due to this storm. So that was an extreme event caused by such a compound effect. Speaking about impacts, I will just quickly say this also from the SREX report. They talk about impacts. It's not only about climate and weather, which is the left part in this diagram. It's of course a lot about exposure and vulnerability also. So the impact of such an event, it really matters what kind of society it hits or what kind of ecosystem it hits, of course. This is quite easy to understand. Natural variability comes into play here also. What is the natural variability? What is a 1,000-year rainfall event in Sweden? We don't really know. We have some observations and we try to have ideas about it, but it's not so easy to say. The amount of data, again, I get back to that, is limited to look at these really very rare events. To the right, there is things talking about climate change adaptation and the management of disaster risk, etc. So it's really much where the society comes in here and how they should act on this information. So the last slide now on these assessments. There have been assessments in the IPCC reports, for instance. There are 4 of them down here, and they in the 5th assessment report, I had this table comparing them a little bit, looking at different types of extremes. And in green here is a very short summary in very simplified words what we really see in the observations. We see more warm extremes, of course, less cold extremes, etc. And these are things that were now written down at the latest time here in the last IPCC report a couple of weeks ago. I will not say anything more about this global large-scale pictures or anything what's happening, but you can go to that literature to read more about it. But I will give one kind of advertisement here about things that are ongoing, which I find quite interesting. And it's about how to try to explain these extreme events from a climate change perspective. There is a lot of a growing field now in science called attribution, where you try to look at these also single events to say to what extent they might be caused by the changes in the climate that human mankind has had on the system. There is annually now a special issue of the BUMS coming out, talking about these studies, attribution studies that have been published in the year. And that is a growing volume. So now, I mean, it has grown from some 10 papers in the beginning. Now I don't remember if it's 30 or 40 in the last one, and there will be a new one of these coming out quite soon. They are quite very interesting to read, these papers, and I would highly recommend to look into them. There is also the World Weather Attribution Project. There is a link up there, and you can look that up. If you go into their homepage, you can go in and look at projects and analysis, and you could, for instance, look at the heat wave in Sweden or Northern Europe this summer, or the drought in South Africa and things like that. So they are quite rapidly trying to assess to what extent these features are caused by global warming. This will likely be converted into some kind of operational service within the Copernicus climate change services within maybe a year or something like that. This is what you need to do to work with a attribution study. You need to study something they call the counterfactual world. This would be pre-industrial conditions. To do this, you need climate models, since you don't have the information from observations. So you need to have some kind of climatological or climate models there. You also look at the actual world, and then you can look at probabilities to say something about to what extent has the risk of such a summer as the one we saw here increased in Sweden due to climate change. So that was the very general part. Now I'll go into the example. We will look at southern Sweden, a very heavy rainfall event in the last day of August in 2014 in the Malmö area. I don't know if anyone was there at that point. You probably got quite wet, I guess. These are some observations from that day. In like 6 hours or so, a major cloudburst passed this area, and there were more than 100 millimeters coming down in that time. In Malmö, in a year, you have 700-800 millimeters. So it's really a big amount of water coming down in just a few hours. The observations are these red dots from the cities, the city measurements, the city water protection agencies, and people working with water and sewage. They have some measurement equipment here and there, so they are collecting information on a high temporal resolution, so they can really look into these numbers. While the SMHI, we only have two stations, one here in Falsterbo and one in central Malmö up there, and they are not that high resolution in time. So the amounts of observations is one thing I want to highlight here. Even if there are quite some observations here, it's still quite coarse compared to the structure of this rain. This is a radar image of the same occasion or the same kind of rainfall, and you can immediately see that some of these very red dots on the right-hand panel there, they fall outside of the observations here in this one. So there's a problem of capturing such events, and this is now a rainfall event, but it could also be something else. So what happened in Malmö? Here are some pictures, some impacts. It was wet. And it really changed the way as how we really perceive these extremes. And I mean, it rained 2 times as much as what previously was considered a 100-year event. So it really came really outside of all of the curves that we have from before and statistics. There were many different reports on damage. It costs enormous amounts of money, of course, and there were, this picture here shows all of these basements that were flooded all over the city. So it was a major weather-related event, but then it was not just the weather actually causing all of these damages, since this is one graph saying something about exposure and vulnerability of Malmö as well. So here you can see all of these black dots. These are reports about basements that were flooded in this event. Down here you have the precipitation map again. It's quite homogeneous over the area. The largest amounts are down here, which is in this area here, basically. But the dots are up there in the pinkish areas. And these are the areas where Malmö has the old sewage system, where rainwater gets into the sewage system, and then it gets up in the basements where people live if it rains too much. So this is kind of a map saying something also about the vulnerability of the city for this kind of event. So that was one case. Now I will say something about some climate modeling results at the end. We'll continue with Malmö actually, and this is a particular case. So here we have 4 pictures showing something about rainfall in Malmö on that very day. The upper left one shows observed precipitation, now from SMHIs and the other stations from Denmark and Germany. You can see the red and the pinkish colors there, these are the two ones that we saw on the previous maps with the really high amounts. You cannot see the numbers on the bars, but it's quite intense precipitation, I promise. To the right, you can see an image derived from weather radars, where they have collected information about the intensity of precipitation. And you can see this event really sitting on top of Malmö, more or less, and it ran through there quite in these 6 hours, producing all of this rainfall. Now, at the bottom, you have two weather prediction models. And we can start with this one here. This is the high-resolution operational model that is being used at SMHI to produce weather forecasts. It happens to have a precipitation area close to Malmö. This is to a large extent by chance, actually. But it's not so interesting where it really sits. To me, the interesting thing here is that this model can really reproduce a lot of features of such a system. You can get the intensities and the kind of format and shape of such an event. So it tells me something that these kind of models, they can really say something about heavy rainfall events. Which is not the case really for a global model or a core scale model. This is now the ECMWF forecast model. There is no really strong event in this case, but I can assure you if it captures some strong rainfall events, it will not look the same as that one. You will never get the same gradients, and you will also not get the same intensity. So it's quite clear that these small scale models are doing a much better job here. So here we have some statistics now with the operational model that we are using at SMHI. Here we have run it in a climate mode over Switzerland for a large number of summers at different resolutions. And you can see when we compare, this is now intensity of precipitation and this is the frequency. So if we're getting out down here, low frequencies, high intensities, these are the high intensity rainfall events we are most interested in. You can see the observations of the black things here. And to a large extent, the high resolution model really captures this kind of behavior, looking at high intensity rainfall events. While more core scale models, like the blue one here, which is of the same order of the resolution as most of the climate, what we today call really high resolution models for Europe, are at resolutions like this. So we see a large improvement when going to these very fine scales. So basically what I'm saying now is that all climate models that we are using, regionally or globally, they cannot represent this kind of high intensity precipitation. Now we will apply this in a climate change experiment. I have 2 more slides, then I'm done. So we use this model now for 2 areas, one over Scandinavia and one in Southern Europe as well. And there was an additional experiment at KNMI in the Netherlands also looking at an area in Central Europe. It's not in here. So we selected a number of really wet months in the beginning of this century. It was selected from observations, a number of summer months. The reason for just selecting a few is that it's really computationally really expensive to run these models at this high resolution. So we couldn't do a long period. We just did a couple of months. So we made downscaling first of reanalysis. This is more or less the observed climate in 2 steps. First, at a relatively coarse resolution. This was like about 12 kilometer grid scale over these red areas. This 12 kilometer is what is used in something called Eurocordex, where we have a lot of regional climate models for Europe. This is the best resolution existing today with large ensembles of climate model simulations. And then we looked at the high resolution simulation now with this HCLIM. This is the climate model that we're using at this really high resolution in the black areas of Scandinavia here and also in the southwest. And then we made an additional experiment for a surrogate warming experiment where we added actually 2 degrees to all of the boundary conditions. So it simulates a warmer world. We also made some changes to specific humidity, etc., to keep the relative humidity constant. So we had a warmer climate, mimicking the future conditions here. And here comes the results in one slide. So what it shows here is that with a coarse scale model, this is the kind of standard regional climate model, we see an increase in heavy precipitation. This is now the 99th percentile of wet hours in the simulation over all of these 20 or summer months or so. So we look at precipitation changes per degree of change in the dew point temperature. So we can see relationships here of the order of 5 to 6% per degree of temperature, which is relatively close to something called the Clausius-Clapeyron relationship, which says something about the relation between water vapor content in the air and temperature. If we now do the same thing with a high resolution model, we see a completely different signal here, which is much, much stronger. It's almost double the strength here. And this has, of course, a tremendous impact on everything that we have said before. All of previous climate change simulations and projections looking at these really heavy precipitation downfall or heavy precipitation events are likely underestimating the climate change signal of these events. This is now the fourth model in the world showing these results. So we have seen similar things in the UK, in Germany with the Cosmo model, and also in the US with the WRF model. So I think these results are really robust, and it has a strong impact actually on dealing with precipitation extremes at a local scale for convective precipitation events. Thank you.
Thank you very much, Erik. Any questions?
I'd like to know if this is relevant for other kind of extreme events than cloudbursts. I mean that a finer scale would get a
not necessarily. I mean, there is something in particular that we capture here by going from this 10-15 kilometer resolution to 2-3 kilometer. We get rid of the convective parameterization in the model, so we really more explicitly allow convection to occur in the grid boxes. So there is a shift here in how we really describe the processes. So it's not, you cannot translate it directly to any other process. You need to look into which possible process you gain understanding of, and so there is a fundamental difference.
Okay, so it's quite specific.
Yeah, and also I can tell you here that the UK group, they did a similar study with exactly the same setting of models, and they looked at synoptic rainfall events. I mean, with the frontal systems in connection to low pressure systems, and they didn't see the same kind of amplification. So that's a different story.
Instead of using the uniform 2-degree surrogate model, it would be really interesting to drive it with IPCC scenarios, but especially interesting if you could run enough cases that you could make a predicted climate change version of that very nice frequency diagram, frequency versus intensity diagram. Is there any intention to do something like that in the future? Is that feasible?
Yes, the UK group have done it with some 20-year time slices. They have one scenario, I think. We are cooperating now with the Nordic countries, so we are using the same model system, and we are going to run each and every institute doing one simulation. So there will be a couple of these in a year's time, something like that, and then we can get back to that question.
Okay, thank you. I think we continue now. So,
So can you hear me online? Yeah. Hey together. Yeah, we had some long hair issues today already. So I was asked to present something about future storminess, and somehow I suggested also to slightly add, modify the title and give a brief overview on historical storminess to get a context. And well, what I will present is quite simple. Somehow I will briefly give you an overview about what we know about storminess, at least for Europe, and show you a brief analysis based on a reconstruction I started during my PhD, and a comparison with the 20th century reanalysis. And then the second part is basically on a recent publication where we looked at changes in storminess for the 1.5 warming world compared to 2 degrees. And there we'll also focus on very basic things. What are the changes in the pressure and wind fields, and to which extent do we see extremes? And in the end I try to answer actually the question if some of these changes which we might see in the future, if we already see some of them. First about historical storminess, starting around 1850 50. If you work with longer time scale storminess, then geoscientists might recognize this kind of graphs you get. There's a lot of noise somehow, it looks at least like that. And that's a proxy for different proxies based on sea level pressure from Stockholm. And I don't explain now all the different versions, but they are all based on sea level pressure data. So you can identify rapid changes in sea level pressure, and they are typically linked to storms. And there you can define different things. That was done by Lars Bering, for example. And then you can also use storminess from graded fields, for example, like 95th percentile or from 20th century analysis, and you can compare that. You get a lot of variability here, but if you look at the decadal variability, then you see that they are more or less show here storminess period here is a bit lower. Then there's a slight trend here. Then you have a high storminess period here. And if you go even further back in time, then it gets difficult because then people didn't really measure sea level pressure very consistently. So they didn't read at the same time every day. And then depending on which proxy you take, you get a divergence. I think the most realistic one might be the green one, and that's basically the proxy which is based on extreme changes in sea level pressure from one day to another. And that's the most robust in terms of when you measure, and the others measure 8-hour changes or low, the number of deep lows, and if you don't measure that in a consistent way, then you get the divergence. So basically, that's very difficult to study storminess on this longer time scales. And if you do a review of studies which are based on direct or indirect observations for storminess, it starts 1700 to around 2010 here. And there are different regions: Central Europe, Baltic Sea, North Sea, British Isles, and North Atlantic and Iceland. And the bars just tell you how long the time series is, and the color tells you green, there's no trend in these studies. Blue means that they have a negative trend in storminess, and red means that there's an increase. And if you put that together, then you might see some increase in long-term storminess, maybe in the North Atlantic and Iceland. But what is quite clear is that you actually get a decreasing tendency in Central Europe. That's mainly the region north of the Alps. So to some extent you could say that there might be a northward shift in storminess over Europe based on many of these time series are not completely homogeneous, but the idea is if you take many of them, then you can get a bit more uncertainty. The alternative is actually to look on gridded maps, and that's basically what I do today. And first, somehow if you talk about storminess, it's sometimes not clear what it means. Today I will focus just on high wind speeds related to extratropical storms, so basically the cyclones. There are also other kind of storms which you might also have, for example, during summer related to thunderstorms. That's not the topic of that talk. And in terms of measures of storminess, I will talk about 90th annual percentile of daily mean wind speed. So the wind speed has typically more or less a Gumbel distribution like this one. So for every year you can, for example, look what the wind speed of that percentile is, and then you can make a time series of that. The same you could do for precipitation. It has this kind of distribution. Then you also would discuss that tail. And for sea level pressure, for example, if you look at deep cyclones, then you also use that percentile, and then you can actually infer storminess based on this kind of statistics. Data sets are a bit sparse if you go really back like that. So for my PhD study, I had to do a reconstruction which is based on sea level pressure observations, and I don't go into details, but the idea is basically that you use the pattern of observation data in the past, look for a pattern in the present, and for that present pattern you know the related wind fields, and then you use that wind fields from the modern analog as a wind field of the past, and that's how you do this wind field reconstruction, and that can be done based on very high resolution regional climate model which are redistributed basically in time based on the correlation which you get from station observations. And the second data set is the 20th century reanalysis, and what is important about that, some people use it as observations, but it's not observations. It assimilates only daily sea level pressure, so not like other reanalysis data, they assimilate a lot of different variables also in the vertical. This is only a surface assimilation, and that might cause, or basically it's clear that it causes actually problems over longer times. So the trends are sometimes not consistent here. If we talk about basically the central northern European storminess, you can decompose the wind field in the leading modes of storm variability. And the first leading mode is basically what we typically know. If we have a strong pressure gradient between Iceland and Azores, we get stronger winds. That's the leading mode here, basically shown high storm variability here, and the correlation of wind speed or storminess with the pressure field is this zonal pattern, and that's basically the leading mode is linked to zonal changes in pressure gradient. And the second mode is related to the intensity of cyclones. That's why you get actually here a circular correlation pattern. Basically means if you have here a deep cyclone, the wind speeds will be high here and low here, and if it's a high pressure, it would be vice versa. So if you decompose these, you can create a time evolution of these two components. That's based on the NSAP reanalysis data for more recent time, and that's a standard normalized data set. And here you see this strong storminess around 1990, and that's mainly because of strong zonal changes, so positive NAO. But you can also see that the storminess slightly before was mostly driven by basically deep cyclones. But overall, there's no long-term trend if you add actually the most recent period. So based on that, you don't really see a change in storminess. If you do the same thing for data sets going back till 1850, then it's good to focus on the decadal running mean, and you see again this very stormy period around 1990. And there's also a very stormy period here in the past, which is at least as stormy as that, but there's a higher uncertainty. But there's indication that storminess in the past was as high as in this period. And NSAP reanalysis is shown here. Some ensemble members, they are quite low here and a bit higher here. So they show a long-term trend, and the reconstruction and also other information, they don't show a long-term trend. Another way to look at storminess would be to count how many deep cyclones do you have per year over Northern Europe. And that's basically shown here. And that's basically why you can use different measures, and more or less they show the same. Again, here high storminess and here high storminess. And again, the number of cyclones, of deep cyclones in the 20th century reanalysis is extremely low. It's close to having no deep cyclones, and that's a problem of that data set. And again, here you don't have a long-term trend, but if you instead of the numbers look at the spatial area impacted by deep lows, then you see this unprecedented high spatial impact over Europe. So there's an indication that during this period the storm track moved towards Scandinavia. So that storminess is mostly felt over whole Europe, while this storminess is only partly over Europe. And again, you have this inconsistency in the 20th century reanalysis. And the third thing you can look at is actually if you say, okay, the storminess has moved, or the storm track has moved towards Europe, then you should expect a change in the correlation between the storminess over Europe and the NAO, for example. And here I show a correlation pattern, but the trend of the correlation. So these positive values basically mean that there's an increase of 20% in the explained variance by the NAO over time. And here's actually a decrease, and that's consistent if you say that the storm track moves northeast, then the correlation with the NAO increases. And you can also check that with different independent data. For example, I use here some sea level record or storm surge records. And if you do a running correlation over time here in Stockholm and Cuxhaven, then you see that the recent time it has a very high correlation because the storm tracks moved in the domain, while in the past you don't really have that, with the exception of Cuxhaven here. So there you see a tendency that this northeast shift somehow seems to be a new thing. So the conclusion for that is basically we have multi-decadal variability, but no trend, at least in my data set. Also in sea level records and many others, you don't really have a trend. The trends in 20th century reanalysis are not real. So there are several publications. I think that was the first one we did in 2013. And the long-term variations basically of cyclones, there's also no trend, but the question is if this spatial impact at the end of the century is really a new thing. It disappeared now again. The question is, of course, what happens in the next decades. So if this movement continues, we might get actually a change in the storm track. And also that is confirmed by the change in the correlation pattern. So the question is that now a change we see in the past? And if yes, then we would expect to see it maybe already in the not so extreme warming scenarios. And that work is mainly based on the work by Monika Bacikowska. She worked at Princeton and works now at the Environmental Defense Fund. And basically a part of that project was to run simulations for a 1.5 warming world and a 2 degrees warming world, and that's called half-degree additional warming prognosis and projected impacts, HAPPY. And some details about this simulation, they are all atmosphere-only simulations with CAM5, and for the historical part, there are different resolutions, which is interesting to compare. And for the future, basically, you have ensembles for these two different worlds, and then we compare the storminess for that. Briefly about the resolution, here's how it should be in era interim, and that's the storminess into the sea level pressure in 2 degrees. You see that the pressure here is much too high compared to that. So that basically destroys a bit the validity of the storminess. If you go to 1 degree resolution, that inconsistency is significantly reduced. And if you go to a 25 kilometer resolution, it becomes very good here, but then instead the storminess is a bit, or the sea level pressure is too low here. So the 1 degree might be the best option, but the future basically was started on 25 kilometer. For the storm track, basically it's the same thing. If you have too high pressure here, then the storminess is too high here. 2 degrees at 1 degree, it gets much better. And at 25 kilometer resolution here is fine, but then instead the storm is a bit too high over the Atlantic. And talking about the changes now, 2 degrees versus present, you see here there's an increase in pressure and a decrease. That's a positive NAO. And basically that you see also in the precipitation, you get more precipitation here, less here. That's again the northeast shift. And the changes mostly happen after exceeding 1.5 degrees. So most of the changes might come after that. And the same applies for extreme storminess. It will also mostly happen after exceeding that value. And that the same applies for the extreme precipitation event 3 hourly. So this is always this northeast shift. And basically the conclusion about that is you see already again this northeast shift. Most models show that. You see a shift in towards NAO+. Not all models agree. You see intensification of extremes north of 50 degrees. And most of the changes will happen after exceeding 1.5 degrees. And to summarize, based on the past, we see this northeast shift in storminess, and somehow we see it in the future. So to some extent, you can argue that maybe a change has already happened. Thanks.
Thank you very much, Frederik. So there's time for a quick question from the audience. Do we have any questions? I had a question about the resolution, actually. Just quickly, I think you talked a bit about it and you showed these differences that you do not see. You have some difficulty in trusting the models because you see different patterns at different resolutions. Yes. But does this apply equally to all the variables, do you think, that you studied here?
Well, it also depends on which variable you use. I mean, for example, for precipitation, the higher resolution is much more realistic. Was also mentioned in the talk before, so that's also something we see here. But somehow in that case we looked really on the storm tracks, and they depend on this bias in the sea level pressure. And there I think the high resolution is good, but still not perfect. Yeah.
Okay, so there's still some more confidence in the storm tracks than the precipitation extremes, you'd say.
exactly.
Yeah. Okay, thank you.
So, thanks.
Thank you.
Next speaker
Yeah.
is Peter Berg from SMHI again, and he will talk about temporal and spatial scaling impacts on extreme, within brackets, precipitation. Yes.
A little bit, since I'm not
Please.
addressing extremes in particular, but I do mention them. After seeing Erik's presentation before, I will try to also connect a bit to that one, since the topics are quite close to each other. So I will talk a bit about how when you study extremes, the temporal and spatial resolution is quite important, and it can impact your results a lot, especially when you're looking at climate models that work on a coarser resolution. So I'm starting also from an example from Sweden, from a cloudburst. These are from our 15-minute gauge observations. We have, these are the top events that we have recorded since year 2000. And the top event here I want to emphasize, this is in Douglas and in Värmland. We recorded 40 millimeters in 15 minutes. And although this is, so this leads the top recorded events on 15-minute resolution, but also when you go to longer durations, up to a few hours, this is the highest recorded events in this data set. And we will look a bit about what it looks like in scales. So I will show a simulation, not a simulation, but an animation of this event from a corrected radar data set we have, HIPRAD. And then it looks like this, and you will see the event close to the zero. Here is the gauge measurement. And these are 15 minutes time steps, and here the event develops. The gauge is not working for a few steps, but here we have the most extreme core of the event sitting right on top of the gauge. This whole box is 200 by 200 kilometers, so it's a quite small event. And as Erik mentioned when he showed the Malmö case, we have only a few gauges, so typically we have one gauge every 50 kilometers, 50 by 50 kilometers across Sweden. So the gauge is unlikely to capture the core of these events. And you see also that there are very intense cores with red colors here also elsewhere in this animation. So if we estimate what it would look like in a coarser resolution or a climate model, I've simply coarsened the radar here to 16 and 40 kilometer the side of the box. And it looks less and less impressive, of course. But in this case, even the 40 kilometer resolution contains the information from this high resolution event, of course. That's not obviously the case in a climate model where you don't know if they have actually simulated this in the correct way. So I will show you an idea of how to work with different space and time resolutions to kind of get to retrieve the characteristics of a coarser resolution data sets by using a higher temporal resolution. So if we look at two different ways of observing events, one is the gauge, where you have a fixed location in space. So you have a bucket collecting rain as it passes over the gauge. So we have a time series with some statistical quantity. And the other one would be you have a snapshot, a spatial snapshot from a radar or other remote sensing like satellite. But you don't accumulate in time, but you have the snapshot and you can measure the area of the event instead and get some statistics from that. Going back to the Taylor hypothesis of frozen turbulence, basically saying that the eddies are not significantly developing over the time they pass over the station, you can start to connect different spatial and time scales. So we made an experiment on this over Germany, or analysis of this. So in this plot here we're starting from the green dot here, which is radar information with 5-minute temporal resolution and 1 kilometer spatial resolution. And then we coarsen this. So we have 2 years of data, I think. And we coarsen this to different, to coarser spatial resolution and coarser time resolution. And what I show here is the similarity between PDFs. So we have a distribution of intensities for these different resolutions. And if we start from 25 kilometer and 5-minute temporal resolution data, we can compare the PDFs using some measure. I can't remember what we used here. It's either a Kolmogorov-Smirnov test, or it's just the overlap between 2 PDFs. So if you overlap them, you will have the overlapping area will be between 0 and 1 if they completely disagree at 0 and completely agree at 1. And if we simply compare this at 5-minute resolution to finer resolution at the same temporal resolution, you would see a drop in the agreement between the PDFs. They would start to look different because the fine temporal spatial resolution will have higher intensities. The PDF will move to the left, so to speak. But if you at the same time coarsen your temporal resolution, you will find a ridge where the PDFs look similar. So, and we can calculate this numerically and find an approximation where this 25 kilometer spatial resolution, 5-minute time resolution data compares to a point gauge, which is up here. And that would be, you would coarsen your gauge to 80 minutes and the PDFs would look approximately similar again. So that's trading, if you coarsen your temporal resolution, it will look more like a coarse space resolution. So we can use this when we look at climate models or other coarse resolution, coarse spatial resolution data, and you want to compare it with some high resolution point source data, like station gauges. And then we have 2 cases. We have the what we call the model limited case, where the model has a coarser temporal resolution than the gauge. And to compare to the gauge, we would have to coarsen the gauge to find a PDF looking about the same. And the other case is the what we call gauge limited, where the gauge has a coarse temporal resolution. And we would then have many different choices from our climate model. You can coarsen it in space, or you can coarsen it in time, or a combination of the 2 to find. Is that better? Well, you won't know here. Anyway, they can knock on the roof, maybe. Yeah, so you have many choices here to find an approximate agreement with the gauge. And in this case, you could pick this spot where you're coarsening in time only, but keeping a spatial resolution. Maybe this point would also be fairly similar where you coarsen in space only. And just some numbers on this, not really relating to the plots, to the schematic here, but we calculated with a climate model over Germany, and at 28 kilometer 1 hour resolution, comparing to a high resolution gauge at 1 hour time output, you would need to coarsen the gauge to about 3 hours to have a similar characteristic of the PDF. And on the gauge limited case, we say we have a model at 77 kilometer and 1 hour outputs. We could, and a point gauge at daily resolution, you should not coarsen your model to daily resolution, but you should rather use 19-hour resolution to compare with the gauge. So let's see. Yes, and to relate a little bit to, well, I didn't know this, but anyway, since Erik talked about it, I will relate a bit to climate models. So this is a study that will soon be submitted to, I mean, we'll see if they accept it, but you can check out NHES discussion papers in a few weeks, where we looked at the Eurocortex ensemble. So this is 12-kilometer resolution simulations, and we looked at hourly outputs from these. And we calculate depth duration frequency, so return values of, so here I show 10-year return values for 30 years of data. And up here, this Kostra image of Germany is observed 10-year return values. And you see that the Black Forest sticks out a bit with higher intensities, the pre-alpine region, and a bit of a decreasing intensities towards the north in the country. And if we look at these different simulations, there's a bunch of RCA4 simulations. There's 2 RACMO simulations from KNMI, Hirham and Remo from Denmark and Germany, RCA4 of course from SMHI. And it doesn't look very good, right? They have much too low intensities. I'm losing this one. Yeah. 2 minutes, okay. And these 2 models, the Hiram 5 and Remo, have a bit the better intensities, but as you can see, they fail completely on the spatial pattern. None of these simulations have these orographic regions where they should have these events. And compared to what Erik showed, this is long-term statistics, so they should really do this. But of course, we are at hourly, and then these convective parameterizations, it's a resolution issue. The models are not, they cannot capture this. But if we look at 12-hour duration instead, then these patterns, orographic patterns, starts to appear. And as we know from earlier studies on daily resolution, they look fairly good then. So, and the 12-hour duration, we have a kind of different, we're not really in intense cloudburst regime anymore, but a bit larger scale events. Okay. And in this paper, I also look at this, how it connects to future and how the events scale, similar to what Erik showed, that they, but a lot depending on the RCM, it depends if they scale at below or above Clausius-Clapeyron rate. It varies quite a lot. So another teaser. To conclude, I showed an idea of how you can trade space for time to be able to compare across different resolutions. This is a useful method for model evaluation or for bias adjustment, which the case we make in the GRL paper I presented. And the main issue is that the model must still be able to simulate this information, the fine scale information, otherwise it wouldn't be in the core scale pattern. So I don't know. This is the problem with model evaluation still. Okay, thank you.
Thank you very much, Peter. Questions?
Arvid. Thank you very much. You showed in the beginning a picture, a table with the entries of these extreme records, right?
Mm-hmm. For Sweden. This?
Yes. The news data is from 2011. Is there no newer data in this list?
No, there's no extreme topping that event.
Why is that?
They haven't occurred.
All right. Okay.
Now, I mean, in this data, so this is only for 15-minute resolution. Maybe there's one on hourly or 3 hourly. I'm not sure. But when we look, these data start in 1995, about 96, and until present, and we don't see any increasing trend in this data. It's too short a period for this.
Interesting. Thanks.
And you can read more about this in a report from SMHI on Skyfall.
Yeah, thank you. It's a little bit connected to the station density, so I was wondering if you could use private measurements. Is that something you would be interested in or something you're looking in?
Yes, it's very interesting. It's also very challenging for homogeneity and simply the quality of the measurements. We are collecting a lot of data from kommuner, like municipalities, but some are very good and some are very poor, not quality checked sufficiently, so it's very difficult to use.
Okay, thank you very much, Peter, again.
Yes, so welcome to the next talk, and it will be a very different view on impacts of climate change. So it's not about extremes, but it's really about the impacts, but not about the usual way we think of impact, and we think, yeah, maybe we have more heat waves or whatever. But what I will talk about is whether climate change will affect our ability to make weather forecasts, and kind of not dependent on certain models or so, but really will it in the future, due to climate change, be easier or harder to make weather forecasts? That's kind of the question I will try to answer. Oh, sorry, I was run around a lot, so you have to get me back. And then when we talk about difficulty of weather forecasting, there's one key concept I have to introduce first, which is weather forecast uncertainty. That's kind of the realization is that all weather forecasts are to some extent uncertain. That's something we usually know from experience. We just know that whatever forecasts we use, they're not always right. And that's quite well understood why this is. So Lorenz already pointed this out in 63, that it's kind of inherent in the atmosphere, so it's not only a technical problem. And the reason is this: if you have like very small errors in your initial conditions of your forecast, or if your model has just some small errors, then they can grow really big and kind of cause problems in your forecast. And but then one important thing is that so all weather forecasts are uncertain, but not kind of the degree of uncertainty, so it's not always the same. So this depends a lot on where you are in the world, on which season you are. For example, it also depends on weather regimes, which is something more dynamical, and it also depends on your model. But if you're really in the fundamental thing, we know it varies from place to place and from day to day, which then opens the question, okay, so then does it also vary with climate change? So if our atmospheric system changes in some way, maybe also our the typical uncertainty in weather forecasts will change. And so that's kind of that's the research question. I will always talk about uncertainty, and then you can kind of more or less translate it to difficulty, kind of to have a simple term. And now one more slide on this concept of weather forecast uncertainty, because there's a relatively well-established way to define the uncertainty in certain weather forecasts. And this you do with so-called ensemble weather forecasts. So you don't make one forecast, but you make a couple of forecasts, and then you look at them, and if they kind of all say the same, which we have to write here, so here we start, and then we make a couple of forecasts, and if they kind of all more or less say the same, then in this particular case we are quite certain that this forecast will be true. So in this case, the uncertainty in the atmosphere is low at the moment. The uncertainty is low. And we can also have the other situation that the forecast all show something else, which means it's very hard to make a good forecast. So in this situation, the forecast uncertainty is high, and then you can easily quantify this. So you have your forecast, for example, of temperature or sea level pressure. Precipitation is a bit more tricky. And then you simply compute a standard deviation at a certain time ahead, for example, 6 days ahead. And then you have the standard deviation, which we usually call a spread. And then in this case, if the spread is high, it's kind of more difficult to make a forecast. And if it's low, it's somehow less difficult to make a forecast. And what I now want to know in the future compared to today, will we have relatively more of these or more of these days? So that's the kind of the question, which of course opens the question, how can we address this? So I already said that kind of the way to quantify weather forecast uncertainty are these ensemble weather forecasts. And then as we have seen already a lot today, and most of you know, kind of one of the standard ways to say anything about a future climate is to use the climate model. And then what I did, I combined these two things. So I have a climate model one. In this case, it's the Easy Earth one, standard TMIP5 one on the business as usual scenario, so SAP 8.5. And then because in the climate model, you also have kind of some type of weather, and even though you should never really treat it as weather, so if you look at, 2090, you will have a kind of certain weather situation, but this doesn't tell us about kind of what the weather situation will be on this exact type of day, but still the statistics are hopefully right. But this also means that instead of initializing our ensemble forecast with real observations, which we usually do, we can initialize it with kind of the atmospheric state from the climate model. And this we do, we start in the kind of the past of our climate model in the historical period. We take one day, feed it into an ensemble weather forecast model, make an ensemble weather forecast, and then we have a spread for this day. And we do this for the next day, and we have the second spread and so on. We do this for all days in the historical period. And then we have a climatology of forecast spread or forecast uncertainties. And then we do the same in the future. And kind of, I haven't written down it, but I use kind of 30 years of kind of days in the past and 30 years in the future. Then we also construct kind of in the same way a climatology of forecast uncertainty in the future, and then we can compare them and see whether they are different. And which leads us to the results. And as main variable, I will show sea level pressure forecast, and even though we usually don't feel sea level pressure very well, it's kind of a good proxy of the kind of general weather situations. If you look at weekly forecast, for example, for one-day forecast, it's not so interesting. But everything we do here, also due to the model limitations, is kind of, let's say, on the order of weeks, so typical medium range forecast, we would say. And here on the top, this is simply the past climatology of the forecast uncertainty in sea level pressure. That the typical thing is you see in the exotropics, it's higher than the tropics, which is also true in kind of real forecast, so this makes sense. And you also see the storm tracks. And then here, this is kind of the main result of this study. That's the relative change in the forecast uncertainty in the future compared to the past. And blue means that the forecast uncertainty in the future part of the run is lower, and red means it's higher. And then what is immediately striking, you have kind of a dipole pattern. So in the exotropics, especially in the northern hemisphere, the forecast uncertainty decreases, and at points this means it's significant at the 0.02 level, so this is highly significant, and red means it's increasing. And I will in this talk not focus on the tropics because that's a bit tricky. There's one thing that the model is not super suited for this, and also sea level pressure doesn't tell us much there. There we also need to look at wind and temperature forecasts. So we will kind of focus on this northern hemisphere signal, which is kind of the strongest here. And I have not shown the plots, but if you make these plots, if you look at instead of sea level pressure at geopotential height at 500 hectopascal, which people like to look at when they evaluate weather forecast, it's quite the same. And if you look at wind speed, it's also kind of similar in temperature as well, so especially in the northern hemisphere. So this is kind of robust. So the kind of the large scale weather situation, the uncertainty really decreases in the future one. And now this is all for day 6 forecast, and kind of the scale it's kind of plus minus 5%, and we will immediately see how much this actually means. And we'll also look a bit at different lead days just to prove that I have not cherry-picked out this 6-day forecast because we see something there. Here it's kind of the same, but it's the northern hemispheric exotropics mean of all the forecasts, and then the thick lines are the future, and kind of with the thinner color they are the historical ones, and also split up by seasons. So always kind of one color is one season. And then you don't see it in the beginning, but if you look at the data, it's the same. The future one is always below the historic one, which means that kind of at every lead day on average, the forecast uncertainty in the future is lower than in the historic scenario. And it's also across all seasons, but it's strongest in winter. And now this also gives us the possibility to see a bit, we saw this, it's 5% change, but it's somehow hard to tell what this means. And here kind of convert this to a time scale, which I have done here. So here I plotted kind of the difference between these two lines. So here the time. And for example, if you look at the winter, which is the most extreme, so this means that an 8-day forecast in the future will be kind of roughly as good as a 7 1/3 day forecast today. So you have kind of a lead time gain, if you call it like this, of 2/3 of a day. And in the other seasons, it's a bit less. So it's kind of roughly between 1/3 and 2/3 of a day, kind of to put this in context, how much this is. And now this is kind of a purely numeric result, but we at this party also managed to explain this, which is quite nice, I think. Because we know that one thing is that is kind of driving the mid-latitude weather is the temperature gradient between the equator and the poles. And we also know that this is going to decrease in the future due to Arctic amplification. And now here I have a scatter plot only of the historical ones between the meridional temperature gradient and the forecast uncertainty. And now everything averaged across one season, and then each point is one season. And then we see kind of for all times of the year except for summer, there does not work. There's kind of a correlation between the meridional temperature gradient and the typical forecast uncertainty in this one particular season. And then if we extend this to the future, so ignore the white plot first. Now I also plot the future ones, and they kind of quite well line up with this. So there's apparently this connection simply in the historical one between temperature gradient and forecast uncertainty, and then in the future one, the temperature gradient, also probably not on the video anymore, is significantly lower, and then also the forecast uncertainty is lower. I mean, that's not a die-hard proof, but I think it's at least a suggestion that the reason for this decrease in forecast uncertainty is simply the decrease in meridional temperature gradient. And kind of one additional thing is here, if you now look at the southern hemisphere, where we saw there's much less changes in the forecast uncertainty, that's also kind of congruent with this theory, because in the southern hemisphere, there's also no change in the meridional temperature gradient, which is nice. And now here I could stop and it would be like a super coherent story, but unfortunately it's a bit more complicated, because I have not yet at all talked about precipitation. So I included one thing about precipitation, because you can argue that like precipitation forecasts are really important. And here we then look at 6-day precipitation sums, which is something then you at least reasonably can do with this model. So we've seen a lot today that if you look at precipitation, you need super high resolution models. That's all quite coarse. So that's kind of, you have to take this a bit with a grain of salt. But then still, if you simply look at the change in the spread, so in the uncertainty of 6-day precipitation sums, it looks super differently. So we have a really large signal between kind of -30 and +50%, and it's all significant. And this was a bit striking when I saw it. But then I realized one thing. So here, the spread is also computed simply as the standard deviation, and then it's, for example, it's the absolute spread in millimeters. So if you have, let's say, 10 millimeter forecast, you would say it's 10 millimeter ±5. But in precipitation, it also makes sense to look at relative spreads, because here to the right, I plotted from the climate model simply the change in precipitation, kind of in the climate model, and then you see this looks very similar, so both the magnitude and the patterns. And this means, for example, here in the Arctic, in the future scenario, we have much more precipitation, and then also the spread is higher, which you expect. And then it makes sense to look at the relative spread instead. So for each forecast, I compute the relative spread, so I convert it from 10 millimeters ±5 millimeters to 10 millimeter ±50% it would be. And then I look at the change in this relative spread, and then it's much smaller. So here the scale is smaller. It's only from -20 to +20%. But still, there are signals, and kind of the strongest one is here above Europe, interestingly, where the spread is increasing. And this is kind of completely different than for the other variables we had looked at. So I mean, the kind of uncertainty in precipitation forecast seems to be increasing, and I won't show it here, but we also split this up in seasons to try to explain it a bit. And this is kind of, most of this is caused in summer, so it's really the summer precipitation that gets more uncertain, and we think it might be caused by certain convective situations in summer, which are very hard to forecast, because there in general can be, you can get either no rain or you get kind of a super strong convective event, which is already very difficult now and also in the historical period. And it might be that because there's more moisture in the atmosphere, this gets kind of even harder in the future. But then remember that the model kind of for this type of things is not super suited, so this has to be taken a bit carefully. But still, we can have these two conclusions. So I call it here the practical predictability, which is related to uncertainty, but some people can get very picky about what predictability means. We can also just call it kind of the difficulty or the easiness of weather forecasting of synoptic scale. This means sea level pressure and temperature patterns might increase through climate change, and there might be inside the term because we only used one model, so this we also should kind of acknowledge. And
the decrease would lead to slower moving waspy waves and more persistent weather situations, which in a way could mean that you have fewer impact of fronts for the precipitation of the large-scale precipitation on more convective precipitation. Could you comment on that?
That's a very good point, I think, because it would also be congruent with the fact that we mainly see this in summer, where the kind of influence of fronts is low anyway, and then kind of the extreme way would see kind of the fronts don't play a role anymore, and it's just the convective things which are really hard to predict. So I think that's a good point, but we hadn't thought about this before.
Okay. Any more questions for Sebastian? Okay, well, we'll move on. Thanks again, Sebastian.
Our next speaker is from Physical Geography, Ian Brown, who will talk about identifying atmospheric circulation and climate impacts on vegetation in Eastern Africa. Please, Ian.
I'm going to start with talking about why people go to war. In 2005, I believe, Ban Ki-moon, who then was the president of the United Nations, claimed that the conflict in Darfur was the world's first climate change conflict. And that's a pretty big statement to make. And he made a very clear statement that I think almost no climate scientist would ever make. No climate scientist would ever have the audacity to claim that a war was created by climate change. And a lot of social scientists have thought about this, and a lot of social scientists have done some research on this, and almost none of them, I assume, would actually support that kind of assertion. There's a lot of evidence to suggest that the conflict in Darfur was at least in part caused by a change in resource availability. So perhaps we can say that resource availability deteriorated to a point where we have social conflict, but assigning social conflict purely to climate change is perhaps something that we can't really agree on. Because I'm interested in looking at how we can use satellite data to map vegetation change, we decided to take a look, and we got some money from CEDA to do this. We had a simple hypothesis. If climate change caused the conflict in Darfur, we should see a clear deterioration in the vegetation signal in satellite imagery. And that should be a tipping point. And if there's no clear tipping point, then we can't make such simple attributions. So we take 700 plus satellite images, 2 a month, over a period of 2.5 decades. And we look to see if the area where the conflict broke out suffered a significant deterioration in vegetation growing conditions or vegetation productivity. And if we assume that the conflict broke out in February 2003, which is the commonly assigned period, then what we should be looking for is a tipping point around February 2003, where we see significantly reduced vegetation productivity, in this case in terms of the normalized difference vegetation index, and we actually see no such thing. In fact, if you look at the time series going back to the 80s or perhaps even the 1990s, we see generally a weak increase or no trend whatsoever. So there's our outbreak of conflict, 2002, and what we can actually see is the productivity of vegetation just previous to the supposed, or the outbreak of conflict is actually above average. So then it becomes really hard to say that conflict in Darfur was caused by climate change, because actually what we see is no significant change in vegetation. If there had been significant decreases in water availability, we would see decreases in vegetation. If we saw overgrazing, we'd see decreasing vegetation. If we had reduced primary productivity, we'd see decreased vegetation. We see none of that. But what we did see is some interesting peaks and troughs in the data. We see, for example, at 1998, when there was just after the severe El Nino of 97-98, we see really significant reductions in vegetation productivity. And we see in 1989, one of the local peaks. And that starts to get quite interesting. So we became interested in trying to work out if we had circulation effects on vegetation, or if we have other ways of assigning or attributing vegetation change to weather and climate. So along came Roland Schrager, very clever chap. He put together a time series of 50,000 Landsat scenes, which works out at a few trillion pixels, covering Eastern Africa, Southern Africa, and Madagascar. And we're interested in these regions because we had disruption to the small and long rains in this region of Africa, and here we have sort of a breadbasket area of Southern Africa, and we just started a project on Madagascar, so we added that just for the fun of it. We're talking about 35 terabytes of data here, so nothing you're going to process on your laptop. And in order to compare images from different periods and different satellites, we have to be very, very careful about how we pre-process the data. So what we've done is we've done this all in the cloud because it's 35 terabytes of data. We've taken data from weather satellites, total ozone mapping spectrometer, MODIS. We've done very careful correction of atmospheric influences on our data. We've cross-calibrated against the sort of gold standard, which is LEADAP's processed Landsat 8 data. And from that, we've calculated the normalized difference vegetation index. And because of problems with the environment that we're doing, we've had to just reduce our sample size down to 2.5 billion pixels. Each pixel is 30 by 30 meters. And then we're going to compare it against known El Nino events. So this is a table that shows whether or not we have El Nino or La Nina conditions, or if we have neutral conditions. And specifically, we're going to compare 2015, 2016 to past events. So El Nino in red, La Nina in pale blue. And we want to look at whether or not the 2015, 2016 El Nino was strongly impacting vegetation, where and to what degree. We can see vegetation and precipitation anomalies for the period of our El Nino event, and we can look at, we divided Africa up, or parts of Africa up into different zones just because we have problems extracting the data from the Google Earth Engine environment. Right-hand side is precipitation anomalies, where orange is a negative anomaly, blue is a positive anomaly. Left-hand side is vegetation. Again, red is a negative anomaly, green is a positive anomaly. And what we can see is really clear patterns in vegetation change over our time series. Our time series goes back to 2001. Particularly, we see the planting season. We have massively negative precipitation, and we have very, very low vegetation signals. And this matches analysis done by the US Department of Agriculture, which found 50% less area planted for corn. Corn yields in the following spring or the following growing season down by 47%. So the breadbasket of Southern Africa was really strongly impacted. But of course we have local patterns of variance. We see some areas where we have positive precipitation anomalies, and we have some areas where we see even positive vegetation anomalies. Our data is on 30 meter resolution. So we can actually resolve local patterns of vegetation, and we can separate out natural vegetation from artificial vegetation or agricultural regions. This is an example from the Okavango Delta, where we can see how we have the 2015-2016 event versus years that aren't classed as an El Nino event. And we can see the intensity of the event relative to other El Nino events here, where obviously the reds are negative. So what we see here is that yes, indeed, this was a very, very strong event. Because we have this high resolution data, we can also start saying, okay, let's look at just the natural signal against the agricultural signal, because let's remember parts of southern Africa are actually quite agriculture intensive, and they do employ irrigation, artificial irrigation. And this is what we see here. We see a general trend where most fields, this is southern Zambia, most fields actually have, or a lot of fields actually have, a relatively positive signal. Non-agricultural areas have a very strongly negative signal. So what we can see is with this kind of approach, we're able to resolve at the local scale differences between natural vegetation and artificially irrigated, and that gives us greater confidence in our ability to resolve differences over the landscape. We can look at the Horn of Africa, and we start to see a slightly different pattern. We see slightly positive vegetation and precipitation anomalies, and on Madagascar we see something of a disaster in terms of precipitation in the dry lands west of the mountains around here. So all this is dry lands. We see strongly negative precipitation. We see locally increased precipitation late in the season. With this data, we would actually like to be looking another 3 months forward because of the pattern of precipitation, but unfortunately we didn't have data to support that. So we can look at the intensity, and we see that the El Nino event of 2015-2016 has a large-scale regional variance. We see a very, very strong, very intense El Nino event, and we see a degree of uncertainty in whether or not or how we can attribute that. 2015-2016 was a very unusual El Nino event. Often we would expect the pattern of precipitation to be really quite different. This El Nino coincided with an unusually weak Indian Ocean dipole event. Indian Ocean dipole is the circulation in the Indian Ocean that affects circulation patterns. And what we see in this event is that IOD is unusually weak. Strong El Ninos are usually associated with strong IODs. But this El Nino was unusual in that we had the western pulse of warm water, the sea surface temperature anomaly measured by satellites, came much closer into the African coast, disrupting the normal pattern of precipitation. And this is partly why this event really struck parts of Africa very, very hard. So what we find is a great deal of complexity in space. Here looking at different monthly composites. We also see a great complexity in time, with 2015-2016 being really, really quite an unusual event compared with more recent events. And what we can see is the possibility that the circulation, that El Nino, La Nina circulation and Indian Ocean dipole have some degree of connectivity, that either this super strong El Nino event weakened the IOD, or that the IOD has some kind of connection to the circulation in the IOD is connected to this El Nino event. Our final point is that using Google Earth Engine, we get some great opportunities to analyze gigantic stacks of data. As I said, 50,000 Landsat scenes, 35 terabytes of data, intensive scripting to process the data. Unfortunately, as you've seen, we've got some really quite ugly graphics. Google Earth Engine doesn't support nice visualization and makes it very, very difficult for us to actually extract proper representative statistics. So this is a work in progress. We are hopefully gridding or tiling all our data to be able to extract it, but at the moment we're only relying on a relatively small number of sample points, so 2.5 billion pixels over about 50 sites. Okay, thank you.
Thank you very much, Ian. Questions?
Okay, yeah, it's very interesting. I'm just wondering, are you particularly focused on certain months, or you have everyday satellite and make annual mean, or?
No, none of these satellites are flying over on a daily basis. So we're using 3 monthly composites. So yeah, all our data in composites are 3 months.
Have you looked at the situation in Syria? It has been claimed there also that the war was initiated or at least stimulated by drought.
I've reviewed an article on that, but the data they were using was rather strangely sampled. So I don't know if the article came out or not, but yeah, I mean, there's one problem we have is the modifiable area unit problem, where we do things like we sample over geographic boundaries. So the initial study that I did, we sampled over regional boundaries in Sudan, but unfortunately a lot of regional boundaries don't correspond to natural geographic or precipitation units. So a lot of work that's done on the meteorology in East Africa is done where they actually spend quite a lot of time trying to identify homogeneous meteorological units. The work that's been done in Sudan hasn't done that, and they use political boundaries, and political boundaries are really, really poor at representing both vegetation and weather properties. So it's been done, I know it's been done.
Okay, one last question.
Yeah, the big data aspects of this are really interesting, and some of the techniques might be useful for analyzing huge data sets of high resolution model output. I was wondering, is the data in Google's cloud, and does somebody have to pay for that, and roughly how does that storage aspect work?
It's in Google's cloud, and you're free to process. They have already stored. You can upload data, but they also have large stacks of NASA. Basically, have as much of NASA as they can get access to, NASA's data archive. So that's all the meteorological satellite data, all the Earth observation satellite data. The problem has been that they strongly limit your ability to extract results. So that's why our figures have those sort of pseudo-randomly distributed sample points. What we're hoping now is that they'll allow us to tile and extract through a tiling process, but until now that's not been possible.
Okay, thank you very much.
My name is Malin Norderman, and I work as a nature conservation specialist at Sveaskog, which is a state-owned forest company. And I'm here today to talk about one topic related to extreme weather events, and that is the forest fires that took place this summer. And I'm going to talk a bit about how to monitor these forest fires, and also how we did to look at the post-fire impacts. So this is a bit more of a practical presentation. But I would like to start with looking back 4 years in time. I guess most of you remember this huge fire that took place in Västmanland. It was described as the largest forest fire in modern times here in Sweden, covering more than 13,000 hectares. And 13,000 hectares, how big is that? It's big enough, so you can see it on this map of Sweden. But to make it a bit easier to get a feeling for the extent of this fire, I would like to use a Stockholm perspective, and I hope I don't offend anyone by doing that. So if we take the polygon showing the delineation of the fire and place it on a map of Stockholm, we get this picture. So you can see that we are here right now in Frescati. And this is the extent of the fire. And you can see that it covers a lot of Stockholm and the surroundings as well. So it was a huge fire that affected a lot of people. And this fire is actually the reason I work at Sveaskog today as well. Because at this time, as you heard, I was a student here studying landscape ecology. And I did my master thesis about this fire, looking at forest structure and tree vitality in Sveaskog's part of this area. So anyway, keep this in mind, the extent of the fire, the size, when we move on to this year's events. And if we compare this year's fires to the Västmanland fire, we need to add 75% of the Västmanland fire area to the map, summing up to 23,000 hectares, of which 4,000 was on Sveaskog's land. So this is even bigger, and just to compare this to a normal year in recent time. During a normal year we have few or no fires at all that reach over 100 hectares. So this was really huge. And we had the single most extended fire this year was the one in Ljusdal. It was almost 10,000 hectares. So to be able to monitor these fires, we were of course forced to use remote sensing. And there are two reasons to use remote sensing in this case. And the first one is that these areas are too large to cover and to map in field. And the second reason is that it's quite dangerous to be in these areas. And in some of them, we were not even allowed to be. So we had to use remote sensing to be able to get a feeling for the size and the extent of these areas. And this is an example from the largest fire sites. On the left hand, you can see a picture with shortwave infrared. And on the right hand, you see the same image, the same area at the same time, but showing normalized burn ratio, which is an index used to highlight burnt areas and to estimate fire severity. And you see that we have some red marks here on the images. So these images aren't the final ones showing the final extent of the fires, but these red marks that we have drawn here, they do. And actually it was a colleague of mine who did the analysis this year, so I won't take the honor for this. But using these satellite images, we were able to first and foremost detect new fires, because we receive new satellite images every day. And we were also able to delineate the extent when the fires were put out. And with the help of that data, we were able to summarize the extent on Sveaskog's land. So this graph shows all the fires that took place on Sveaskog's land this summer. And you're not supposed to read all the text here, but as you can see, there are a lot of fires, but there's one that stands for almost the entire area. You see we have hectares here on the y-axis and all the sites here. And Enskogen is also part of the largest site in Sweden, in Ljusdal. So this was the first step of the analysis to map the extent and to see how big it was. And the second step of the analysis was to get more details in these areas, how was the forest affected? Did the trees survive or did they die in the fire? And to do that, we used drones. And by using drones, we get these really high spatial resolution images. We didn't use drones in the largest site, I should say, because it was too large to cover with drones only. So this is an example from one of the smaller sites. And you can see the individual stems here, both that has fallen, but also some areas where trees still are standing. And you can also see the individual canopies and what color they have. And this information was really useful for us to be able to see what to do with the forest. So we used these drone images to classify the forest in different classes. And we classified it depending on if the trees were standing or fallen. And the standing trees were also classified according to canopy color to give us an idea of whether they are going to survive the fire or not. So for example, you can see the small black areas here are areas where all trees had fallen. And the yellow areas are areas where we have standing trees but are mixed colors in the canopies. And this information we used to take decisions on how to handle these different stands. So for example, the stands where all trees were dead, we decided to, as soon as possible, go in to harvest the trees, both standing and fallen trees. But in those mixed stands and stands where the canopies were still green, we decided to do field inventories in all stands older than 60 years. Because remote sensing is great, but you can't see everything using remote sensing. So these field inventories were to see if any new nature conservation values were formed by the fire. And if so, they should be set aside as nature conservation forests. So I guess the conclusion here is that remote sensing is really important in times of these kind of large disturbances, fires, but also storms and insect outbreaks. But I would like to finish off with a more bright side of the forest fires. Because when we talk about these huge forest fires and how devastating they are, I think it's important to keep in mind that seen from an ecological point of view, these fires are not catastrophes. Historically, we had 1% of the boreal forest burned every year, which is 10 times more than we had this summer. So you can imagine the Stockholm map with 10 times more. And the fires create a lot of important structures, such as dead wood and these kind of biotopes with birch and aspen. Thank you.
Thank you, Malin. Are there questions? Yes, I see immediately one here.
When you say that historically 1% of
Yeah.
the fires were of boreal forests were burning in Sweden,
Yeah.
is that a climatic number, or is that a historical human management estimate? So, in other words, how much of that was climate related, and how much was people burning and managing the forest through historical times?
I think it was both, actually, both. And I don't know the exact number, the proportion man-made and the lightened for fire. But one important aspect is that today we try to put out the fires as quickly as possible, and that is also one reason to that number, I would say.
Along the same lines, I've heard that even though this was 23 square kilometers really affected. That was a small number compared to the storm damaged forest every year. Is that correct?
The storm damage.
Yeah, in Sweden, and that we get larger areas that is affected by storms. I don't know.
That's a good question. I found it very hard to see that we have the same area annually that is affected by storms, but we do have storms, but I don't know the area, I'm afraid.
Okay, one final question up here.
I just wondered when you said that field inventories were made to kind of see if there are new nature conservation values. How was it estimated? Because I mean, any ecological values would probably come later. But did they kind of look at specific things that would indicate future values?
I'm not sure if we have started the inventories yet or if they are going to continue next spring, but I think we are going to look at a lot of different aspects, and probably trees that are wounded but survive. They have a higher possibility of reaching a higher age. So a mixture of living and dead trees would be one thing, but also looking at the structure before the fire. So it's a mixture of post-fire structures and how the forest looked before the fire, I would say.
Okay, thank you again, Malin.
So our last speaker in this session is Ninis Rosqvist, who will talk about some aspects of reindeer husbandry, right?
Yes, thank you.
Please.
Okay,
And you're
sorry.
from physical geography.
Yeah, I'm
Sorry.
from physical geography. I would like to start to acknowledge my collaborators here, Pia Eriksson and Carl Österlind, who's Carl is here, and Nila Inga, especially, who is my reindeer herding research partner, with whom I usually give this presentation, but he couldn't be here today. And then Chris Foringer, also from SLU. So we will go to Arctic Sweden, in the north of Sápmi, where we will visit the Leva Sámi community grazing area. There is also where Stockholm University has a field infrastructure, Tarfala research station. So it's out of that field station that we have established the collaboration with the Sámi communities. It started 5 years ago. We're now starting to publish our first results. So meaning that it takes some time to build the trust and to bridge science and indigenous knowledge in this case. Very important work though. For many of us. This is how the area looks like from the top of Lustavara and Kiruna, viewing west into the Kebnekaise. These areas have been grazed by reindeers for thousands of years, free-ranging in the interconnective sense, no borders. Well, that has changed recently. And again, to emphasize that this project was co-designed. The knowledge is co-produced together with the people that are affected by these changes. That's the only way to really understand the impact on the ecosystems, because they have the knowledge to assess the total impact. We can measure things, different parameters, but we cannot assess the whole impact. So it's very inspiring work to do. We'll start in the area that I know very well. I've been the director for Tarfala for 15 years soon. We have monitored the glaciers for 15 years. We understand how they respond to weather and climate change. 5 years ago, we got funding from a network of stations. I'll talk more about that later. So we could expand the monitoring of weather and climate into the other areas of the mountains. But we will start with a graph coming from this place, from Storglaciären, where we measure the snow accumulation every winter. And the weather station also provides temperature data, of course. And luckily, when we were supposed to deal with extremes, we actually have a couple of extremes from this recent year. You already talked about the warming, but I would like you to point out that, so I should first say the left x-axis is temperature. The right one is elevation above the ice surface, which was zero set in October last year. So the blue curve shows how the snowpack is building up over the winter, and it then melts rapidly in the summer. The red curve is air temperature. So we have had first two rather extreme snowfalls in the early part of the winter. I'll come back to those. Lots of snow in a short time. The weather system came from the southeast, unusual up here. It was very local. We recorded this snowfall in a couple of stations, but not to the west of the mountain. So a local effect, in contrast to the very high summer temperature, especially July, where we recorded the mean July temperature was 12.8 degrees. The reference period mean is 6.4. So it was unusually warm. And of course, you also heard how much the glaciers melted. Just to show that this data was useful then when we compared. So this is a cross profile across the grazing lands of Leva Sápmi community from the Norwegian border to the Finnish border. The blue triangles show where we have automatic weather stations operating. They're supposed to operate year-round. We have some struggles there sometimes. But we do now monitor weather changes in the core area of the reindeer movements and the ecosystem that they use. We also use SMOE weather stations to put together this picture. So this is a map showing the grazing lands. Kiruna you see there, you also see Kebnekaise and the location of the weather station. So the blue area is the traditional winter grazing lands to the east of Kiruna in the forest, pine forest, heath forest with nice lichen growth. The yellow is the summer grazing lands extending into Norway, higher alpine area where the reindeers like to be in the summer, grazing fresh vegetation. And in the middle, the spring and autumn grazing areas. The hatched areas are really the core area for calving and rutting. And the red lines are migration routes. They're very important because they connect these different grazing lands. So if you cut them off, they can't move anymore the way they're used to. This is how such a weather station looks like when it's standing up properly. Here's another graph showing snow depth on the y-axis and the time on the x-axis. We have monitored snow change here for 5 years. The breaking curves are due to different battery problems during the cold winter. They freeze and sometimes the satellite modems are not operating well. But you see the same very dramatic snowfall events occurring here, which completely stressed the animals and made them move in the opposite direction where they usually move at this time of the year. So that's two extremes. And I'll show you two other examples. This is the winter 13-14. The upper left is time again on the x-axis and temperature to the left and snow depth to the right. Temperature curve, the blue upper one. Rain on snow events, the orange triangles. Events that are, I should also say that reindeers are very adapted to changes in weather. They have been there for thousands of years, since the last glaciation was there. So that's not the case really here. But in this case, we had rain on snow several times, and then we had a very dramatic drop in temperature. That froze the snowpack completely. The lower map shows the migration route down to the winterland. That went fine. But when that happened, they spread out and left to go to higher grounds where there's other ecosystems providing lichens from trees, desperately spreading out. Then the herders decided that this is not sustainable. They were going to starve, and they moved them by trucks back to the mountains where the snow cover was thinner and they could survive the winter. So that's a typical example of how they had to adopt their methods. Another year we had a winter with less rain on snow events, very variable temperature though, so the snow conditions were not really perfect. And then we had a snowfall event with just a few decimeters of snow, but that meant at that time, because they were already in a bad condition, that they couldn't move. They were just halted. And then they panicked and moved back up to the same higher ground to graze from the tree. And then they were finally migrating back to the mountains in the spring. Oops, now I'm losing this. So I think I managed. Anyway, conclusion from this is that you need, as a herder, high flexibility in land use to be able to adapt to these dramatic changes. And of course, you also have to change the herding methods. Well, at the same time, the flexibility is becoming more and more reduced because of different competing land use projects. You see a number of them here. In this region particularly is mining and all the infrastructure that is associated with establishing new resource extraction. And I mean, we started at the end of the 19th century up here to develop this country. So I'll now show you a range of maps. This is how it used to look like in the 1880s maybe. Then we have mines, some land that is not used, loggings of tree, clear cuts since 2000. We have some more communities built. Defense has a big area, the Swedish Army. We have the railroad, of course, connecting the mining area in Kiruna with Narvik. Then we have the roads. Then we have the power lines. Then we have the snowmobile tracks. And then we have the dirt roads. Going back to the original map, then here we have included buffer zones. So that's a very conservative buffer zone border, 5 kilometers. There are also papers showing that the actual disturbance zone around these activities is maybe 15 kilometers. This is a conservative way. Then we have all these projects and the climate, how climate impacts these different projects. Climate is impacting the tourism here a lot, changing the period when the tourists are using the mountain environment at the same time as the herders need to change their timing when they are about. So there's lots of increasing conflicts and competition for natural resource extraction. Even, well, so in a warmer and more variable future, we know it's going to be warmer, right? We know it's going to be variable. There's plenty of this. This is the winter mean temperature compared for Norrbotten. So it's not looking good, of course. And so what can we do about that? Meanwhile, we reduce our emissions. We maybe should have another think of how we use the other natural resources. This is a map showing, you recognize the land area. The purple squares, the purple markings show expired exploration permits for mining. Areas where there has been tests for minerals. And the hatched ones are actually still active in this area. And it's, of course, there's lots of iron in the ore, copper, and all sorts of other natural resources, forestry, tourism, of course. But there's no way to include all these different impacts into the assessments that you have to make when you want to propose an activity like that. You go project by project by project. You don't include the full impact or the multiple pressures on these landscapes. That's what we have to do. And climate change on top of this is very urgent, actually. What kind of landscape do we want to have up here? So how do you adapt to extremes under these multiple pressures? So what we work, several of us, is to actually, this is complicated, but that's what we have to do. So climate is one thing, but you also have to analyze the full impact. Otherwise, you lose the opportunity for a sustainable future, whatever that is. But I mean, it's going fast, and maybe reindeer herding is not going to be possible in the future here. But then we have to make that decision. That was it. And then I'll list some projects. And I should also say that the funding for the monitoring of weather in these important areas has been funded by the Research Council in Sweden through a network of research stations called field sites. No. Jag gjorde det.
Ahead of time.
So
2 minutes to
yes. Thank you, Ninis.
Yeah.
I see hands raising.
Yeah, this is just anecdotal, but the Sámi I've talked to around Stalowalk say that insects, I mean botflies, are a big issue that's affecting their migration patterns. That it's not so much the mosquitoes, but it's the other bite. I think it's a botfly in English. I don't know what it is in Swedish, but which really attacks the reindeer, and that the season when the high country is free of these insect pests is getting shorter. Is that something that there's quantitative evidence about?
So they go very high in this summer, for instance, because when it gets hot and lots of insects, they move high up on the snow fields to escape them. But it's getting worse. And the snow fields is also a resource that is diminishing in because it's so warm in the summers. Their health, it will be influenced as well. So insects, and they see new insects. that they never seen before, the herders. So there is a sort of a migration of beasts as well. And the predator issue. There's lots of issues that you can't include in such a short speak. But it's an interesting,
More questions? I have one last question. There's been a lot of about the Sápmi and the reindeer herding on the news lately. So have they already start discussing how to change management of reindeer because of not only extreme events, but also if they think about climate change?
They do, but 5 years ago when I started the conversation, I asked about this. That was my opening question. How do you think about climate change? And then I got the reply, I'm not so worried. It's the minds I'm worried about. Now it sounds different. So we were right in time starting to try to understand. And also by monitoring these changes, they understand also more the animal behavior, because they can see that they can couple the weather changes to the behavior, ways that they couldn't do before. But they are very concerned, and they try to mobilize the community. But we also have hunting and fishing, Sápmi, and they're also affected. It's the whole ecosystem. It's not just the reindeers, but they're a very good example because they need a lot of land undisturbed, and we don't really acknowledge that as a resource yet. But I think it's time to think. And also all the feedbacks, grazing, as you know, the grazing influence the carbon balance, and you have how all these kind of system thinking that is lacking in the modern decision procedures.
Yes. Yeah. Thank you very much, Ninis.
Thank you.
To all the speakers, thank you very much.